Today, we're going to learn about fatigue lifing methods. These are the techniques or the methods that we use to predict the cycles to failure under different types of fatigue. There are four main methods we're going to learn about. There's the stress life method, there's a strain life method, there's fatigue crack growth, and there is the two-stage method. Now, our first method, the stress life approach. This was the first method that was developed, originally developed by Euler and Baskin in the early 1900s. In this method, the concept focuses on the relationship between stress amplitude, so applied cyclic stress, and the number of cycles to failure. This method works primarily for high cycle fatigue, when the number of cycles to failure is greater than 1,000 cycles. When we're greater than 1,000 cycles, this means that we're mostly cycling at stresses well away from the yield strength, so kind of low nominal stresses. The advantage of this method is that it is the most traditional. It's the original OG method, and it is the easiest to implement. There also exists a lot of data for materials because this has been around for 100 years. The main limitation of this method is it doesn't account for plastic deformation or crack initiation and growth because it's not measuring anything in the vicinity. It's not controlling anything in the vicinity of those things. And the key idea behind this method is that below a certain stress amplitude, there exists an endurance limit, a value of cycling stress below which a part can have infinite life, meaning it can survive an unlimited number of cycles, right? Now, what does this method actually look like? Well, in the stress life approach, when we run an experiment, we are controlling by the calculated stress in the center of our sample. That calculated stress comes from force that we apply to the ends of the samples. And so we're just cycling that force to a calculated max and min stress until we get to the cycles to failure. Because force is measured remotely and cracks are going to initiate locally and plastic deformation initiates locally, this method does not work well under really plastic deforming types of materials. And so that's why we have to use it when we're greater than 1,000 cycles, right? And this is the main method we're going to learn in this class. Now, beyond the stress life approach, a bunch of people in the 1950s and 60s recognized that we need to be able to deal with plastic deformation and the local plastic deformation when we're near the yield strength or we're above the yield strength. How do we deal with that? How do we predict the cycles to failure? And so the strain life approach was developed in the 1960s by Coffin and Manson. Now, in this approach, it relates the local strain amplitude. So the strains going in max and min locally with the number of reversals to failure. So 2 times or half the cycles to failure, right? This method works really, really well for low cycle fatigue, where the number of cycles is less than 1,000. This is where we have significant plastic deformation. This is where we're above the yield strength and approaching the tensile strength of our material. The advantage of this method is that it can account for localized yielding because we're measuring where yielding is happening. The limitation of this approach is it requires an accurate cyclic stress strain properties, and it is a more complex test to set up and run. It can be difficult to actually perform the experiment correctly. The key idea behind this method is that with this method, we can actually account for both the elastic and plastic strains, the local behavior happening within a component. Now, what does it actually entail? How does this test work? Well, we'll take our sample and we actually control by the local strain in the region where we expect a crack to form and plastic deformation to accumulate. And so we are cycling via the strain. We're controlling the strain until we get to a cycles to failure. Now, usually that's done using a little device called the strain gauge or an extensometer that measures the distance between two arms that touch the sample. And then we just take that measure, and we then find the cycles to failure. From there, we can then create a strain amplitude versus reversals to failure curve, and then plot the relationship of the total strain covering both the low cycle fatigue region, so less than 10 to the 3 cycles, and then but we also can cover the high cycle fatigue region if we use the results from our stress life approach, if we add the stress life results from the previous method, right? And this is a pretty great method for dealing with plastic deformation. So now let's look at the third method that's out there. And this method was also developed in the 60s. This method is called fatigue crack growth, FCG. And this method was formulated in the 1960s by Paul C. Paris. Now, in this method, rather than using stress or using strain, instead it's based in fracture mechanics. It's based in the stress intensity factor of our material. And we look at the relationship between crack growth rates, so how much a crack grows per cycle, with the range of stress intensities from max minus min that are calculated from our geometry. The advantages of this method is it is crucial for damage tolerant design because we can actually calculate how long our crack currently is in a body and say, oh, there's a critical length when this part's going to fail, so we can monitor the cracks and decide when we pull a part out of service. A limitation of this method is that it does require us to know an initial crack size, and we need to know a lot about the geometry and loading conditions. And it can be difficult to actually get the crack growth properties for our materials because the testing is very expensive, rigorous, and time consuming. But the key idea is that we can relate crack growth rates to the stress intensity factor range, the maximum stress intensity calculated minus the minimum, right? So now let's see how this test is run. Well, one thing to consider is we can perform these tests under the control of the stress intensity factor itself. So we know the equation for stress intensity factor, so we can actually control based on that factor related to what we've calculated as the current crack length. So what we'll do is we'll control by that signal what's the max K, the minimum K, and we'll cycle and cycle and cycle until we get to fracture, right? Till we get to cycles of failure. Now to do that K calculation, we put an extensometer that measures how much the crack mouth opens, how much the crack opens up. And then we've got an equation that tells us how much the crack opens up, how much the mouth opens versus how long the crack actually is. And from that, we then calculate K, and then we can do our control. It's a little bit complicated. But what's great about this technique is if we can both map how long the crack is and control by that K parameter, we can then map a fatigue crack growth curve that tells us how quickly the crack is growing as a function of a given stress intensity factor range. And we can then define this envelope with various regions of slow crack growth, stable crack propagation, and then high speed unstable propagation where fracture occurs, right? Now this method, one of the most advanced methods, but also one of the most challenging to deal with. Now, what about that fourth method? Our fourth method is called the two-staged method. And this is a method where we try to combine stress and strain life with the fatigue crack growth method. Now, why we might want to combine one or two of those methods with fatigue crack growth? Well, in the fatigue crack growth method, it assumes that we already have an initial crack size. We have to already assume there's a crack in our body. But in many of our structures, we polish them, they're smooth, there's no crack that's initiated. So instead, what we do is we can use the stress or strain life approach to figure out the cycles to initiate a crack. And then once it's to that size we can detect, we can apply the fatigue crack growth method to figure out the cycles for propagation of our crack and then predict both initiation and rupture. Now, this two-stage approach requires a lot of data and both, many different types of experiments, but this allows us to map the entire 3 stages of fatigue crack growth behavior within a structure, right? Now, finally, how do we apply this as an actual engineer, as a design engineer? Well, the beauty is that all of these methods are useful and they're still actively being employed today for many different applications and many finite element softwares where we actually design components incorporate these techniques to help us predict things like the cycles to failure, cyclic softening and deformation, the crack growth behavior. We can actually simulate a crack growing through a structure and detect the critical crack component when our stress intensity exceeds the fracture toughness and when our component actually overall fractures, which is pretty cool, right? Now, to learn more about these FEA methods and how we can simulate crack growth, check out the supplemental videos in our Machine Elements playlist. See you in the next video.